Okay.
All right. Our next speaker is Chi-Ming Chang. He'll tell us about Fortuity and quantum corrections to Q-cohomology.
Okay, yeah. First, I would like to thank the organizers for inviting me to speak here. And yeah, today I will talk about this paper I have with Yinshen Lin and Qi-Yin, and also some work in progress with two students at Tsinghua and also Enwu Li. So I will first give an introduction to Q-cohomology and Fortuity, and then I will focus on the question of how does Q-cohomology depends on couplings. And then I will discuss the quantum correction to Q-cohomology, and I will talk about a new way of computing the quantum correction by using OPE and normal ordering, and then conclusion. So about the introduction, basically the study of supercharged Q-cohomology in supersymmetric field theory dates back to Witten's seminal paper, Constraint on Supersymmetry Breaking, in '82. And Witten, in that paper, argued that there's a one-to-one correspondence between BPS states and the Q-cohomology classes. And also in that paper, Witten introduced the Witten index, and that's just the Euler characteristic of the Q-cohomology. And Witten also famously argued that the Witten index is independent of couplings. However, how the Q-cohomology itself depends on coupling remains an open question. So that will be the second part of this talk. So this question is particularly important if we consider holography. So the reason is that holography is a strong-weak duality. So on the CFD side or field theory side, the most thing we can do would be some weakly coupled computation. But the interesting thing we want to learn are at the strong coupling. So they are the semiclassical gravity and black holes in the bulk. And so if we can control the coupling constant dependence of Q-cohomology, then we can, of course, learn a lot of this gravity stuff from weakly coupled CFD computation. So as I just said, we can argue that the Witten index is independent of coupling. So we can first look at what are the things we've learned from the Witten index. So these are the things that we did computation at weak coupling, and then we can learn something at strong coupling. And Witten index basically counts the difference in numbers between the Bolzani and Fermioni BPS states. And in many examples, it matches very nicely with the Bekenstein-Hawking entropy in the bulk of these supersymmetric black holes. And we basically this area formula, area divided by 4G Newton. And but if we consider cohomology, it actually has much more information than just index. Much more information than just the number of BPS states also. And one particular information is that if you consider particular cohomology class, you can try to follow that class by varying the rank n. And in this general discussion, roughly the rank n basically characterizes the number of degrees of freedom in the dual CFT. And so usually we have this formula. So the Newton constant goes like 1 over n to some power, to some positive power. And so this means that if we take n to infinity, that means the weakly coupled physics in the bulk. And in that case, if we take a strict large n limit, a strict G Newton goes to 0 limit, the bulk Hilbert space will basically becomes the Fock space of the multi-particle states. And so in this case, we have a very standard holographic dictionary. So on the CFD side, we have multi-trace and single trace operator, and they correspond to, in the single trace case, the single particle states, and multi-trace case, we have multi-particle states. And so holography, this particular dictionary actually tells us something very non-trivial about the bulk physics already. That is, that means if we try to increase G Newton, consider not zero coupling in the bulk, but finite coupling in the bulk. So that means n decreases, and there will be some quantum relation among different multi-particle states. So this is because from the gauge theory side, from this field theory side, the CFT side, these relations are the trace relations. And so if we consider infinite n, so there won't be any relation among different multi-trace formula. But if we consider finite n, there will be this kind of relation. Suppose we have two adjoint scalars, x and y, and considering SU2 theory, then trace x squared, y squared, you can, this single trace, you can rewrite that in terms of double trace. So this means some relation between the single particle states and the two particle states in the bulk. And so due to these relations, naively we would think that there are fewer states in the interacting gravity than the free gravity. But this statement contradicts with our intuition from the semi-classical gravity. So that is because if we have interactions, then in gravity theory, there exists black hole solution. And so these black holes are believed to be the object with maximal entropy. So therefore, the number of microstates of black holes should be much larger than the number of states of these multiparticles. So to resolve this puzzle, let's try to consider the case of supersymmetric black holes. And in this case, whose microstates are the BPS states. And also many properties of these BPS states can be, they are captured by the Q-cohomology. And so if we consider BPS states, we have this old story that so let's try to start from infinite n and let's try to reduce n. And when we reduce n, some of the BPS state would disappear due to the finite n trace relation. So these plots, we have the energy of these states, so they are BPS states, so they always saturate the BPS bond. And this dot means we have a sequence of BPS state, and then they disappears at some finite value of n. If we try to go tune n to be lower than that particular value. But we have another new phenomena, and that is called the Fortuity phenomena. That is, there could be some non-BPS states at large n, and then they become BPS when the gravitational couplings become strong. That means when n decreases to some particular value nc. So this mechanism that non-BPS states, when their n decrease becomes BPS, can be very nicely understood by the Q-cohomology. So the Q-cohomology fall into two categories. Let's denote this curly O to be a formal multi-trace operator. That means the operator at n equals infinity. We do not try to impose any multi-trace relation of this operator. And then this operator O can, there are two situations. One is that if we consider Q action on O, it can just vanish without using any trace relation. And in this case, O will represent a cohomology class at any n. And for this kind of Q cohomology class, we call them monotone class. And so these give us the first case. And so at large n, we get some non-trivial class, so we always get the cohomology class, but that non-trivial class can become trivial class if we try to lower n from large to small. And there's another situation that is when Q acting on O, that gives you some non-trivial trace relation. But that trace relation only show up at n less than some n critical. So that means this formal multi-trace only represent cohomology classes at n smaller than n critical. And that gives us the second situation. If you consider n greater than n critical, that particular formal multi-trace, actually it gives you a non-BPS operator. But if you consider n lower than that particular n critical, that multi-trace can give you a BPS operator. And also, I won't explain, but we can actually count the number of fortuitous classes and monotone classes, and show that there are exponentially more fortuitous classes than monotone classes. And So this comparison is at large n, but fixed energy to be the EPS, and this EPS is fixed by we consider fixed charge and spin. And in this comparison, we do not try to scale the charge and spin with n. So because we have exponentially more fortuitous class than monotone class, that means basically a typical black hole microstate must be represented by this fortuitous class. And so then one hope we have is that by the study of these fortuitous states or fortuitous class, that can reveal some interesting microscopic physics of black holes. So maybe the question we most like to know the answer is what is the typical black hole microstates? And so let me say a bit more of what do I mean by this question. So in the semi-classical gravity, a black hole solution describes an ensemble of microstates. But if we have some UV complete theory, then you may imagine that we might have the power to describe a single typical black hole microstate, not just an ensemble of states. And I think this question is also a question people ask in the fastball program. And so in the fastball program, there are many smooth and horizonless supergravity solutions are constructed, and they are very close to the black hole solution outside the event horizon. And so here I cite a very nice review. And these solutions actually let people wonder if the black hole microstates can already be captured in the low energy supergravity without using the UV string theory. And however, people also try to quantize these solutions and count how many states do we get from that quantization. And the thing people found is that they get much smaller, the number of states much smaller than the number of black hole microstates. So therefore, the states from these smooth and horizonless geometries are not typical. So besides this counting argument, Q-cohomology and Fortuity actually give us a different perspective explaining why the states from smooth and horizonless solutions cannot be typical or cannot be typical black hole microstates. So the argument is false. So if we consider a smooth and horizonless geometry and try to tune the G Newton to small number while fixing its charge and spin and energy. And then rho solution will have a smooth limit. It's a smooth weak coupling limit. And basically these solutions can be viewed as coherent states of gravitons, and if we take a weak coupling limit, they dissemble into gas of gravitons, gas of non-interacting gravitons. So this picture actually fits better with the picture of monotone states and then the fortuitous states. So for these fortuitous states, there are no bulk weak coupling limits because you have this finite N effect, some non-perturbative bulk effects. So this observation actually you can try to turn that to some conjecture. That is the monotone classes, we conjecture them to correspond to smooth and horizonless geometries. And for the fortuitous classes, that I already argued from the counting argument, they are typical. So the dual, we try to make conjecture that they are typical microstate of black holes. And there are some evidence of these conjectures. So you can try to consider some smooth and horizonless geometries and then try to quantize them and then ask whether the state you obtain from these quantizations, they give you monotone or fortuitous states. And for these two classes of examples, we found out that from quantizing these smooth and horizonless geometries, we only get monotone states. So the study of Q-cohomology and the fortuitous states has been carried out in many different examples. So in N equals 4 super Young mills and also N equals 1 super Young mills and also this is N equals 1 deformation from N equals 4 super Young mills. So there's a typo here. And also in ABJM and ABJ theory, and also people study this Fortuity states in D1, D5 CFT, and also SYK model. And also, I think this afternoon we will hear talk from Chi-Ming, and he will tell us about the Fortuity state in some matrix quantum mechanics. And for these theories, people have explicitly constructed Fortuity classes. So for some of them are as small n, and in this SUSY SYK model, we can go to a larger n. And I think for what Chi-Ming will tell you today is, this afternoon, is that for some particular matrix quantum mechanics, you can solve for the Fortuity classes for all n. And these are some partial list of references. So now let me come to the second part of this talk. And I want to focus on the question like how does Q-cohomology depends on the coupling. And I will consider the example of n equals 4 super Young Mills. So that's the example that I can answer this question in a most precise way. So let me introduce some formalism. So we consider the case of a complex supercharged Q, and the Q and its complex conjugate satisfy this very standard supersymmetry algebra. Q dagger anti-commutator gives us Hamiltonians minus some eBPS. So this eBPS means the energy of the BPS states. So they can depend on charge or angular momentum, but you can just consider a particular fixed charge sector so that the eBPS will just be a fixed number. And both Q and Q dagger are nilpotent. So that means for BPS state we have delta equals 0, and that's equivalent of saying that we have Q square equals 0 and the Q dagger square also equals 0. And for BPS states, so H equals eBPS, and the states both annihilated by, so it's annihilated by both Q and Q dagger. And the one-to-one correspondence is this from the Hodge theory argument. So let's consider right-hand side the Q-cohomology classes. That is, we consider the space of Q closed states and model the space of Q exact states. And the statement of this one-to-one correspondence is that for any given Q closed states, you can find some Q exact state and you add to it such that the state will also be annihilated by Q dagger. Okay. So in n equals 4 super Young Mills, we will also use the state operator correspondence. And instead of using state, we discuss operators. And n equals 4 super Young Mills has 16 supercharged and 16 conformal supercharged. And we will just use only one supercharge, one out of the 16, more precisely this Q4 minus. And it doesn't really matter. This 4 minus. Anyway, just choose one supercharged Q. And its Hermitian conjugate is conformal supercharge. And in that particular for that particular choice, the eBPS is given by a sum of 2 angular momentum and 3 R charges in n equals 4 super Young Mills. So let's first consider the n equals 4 super Young Mills with with UN gauge group, and for simplicity. So if we consider perturbation theory at weak coupling, all operators in n equals 4 super Young Mills are UN invariant composites of fundamental fields with covariant derivatives like an X on it. And here I give a list of all the fundamental fields. We have 6 scalar and some fermions and its Hermitian conjugate, and also gauge fields. And so for this gauge field, we can form the covariant derivative. And so basically, you can take this and then try to form some gauge invariant combination, and that give you operators. And now we want to study BPS operator. To study them, we can actually first consider the the fundamental fields, they saturate the BPS bound. I mean, they have delta equals 0. And imposing this condition, we basically pick up some subset of fundamental fields and covariant derivative. They are these subsets. So out of the 6 phi, we have 3 phi. They satisfy delta equals 0. And we also have 3 fermions. And another 2 fermions, I call them lambda. And also a particular components of the field strength. And some particular components of the covariant derivative. So for BPS operator at 0 coupling, they will just be given by a multi-trace formula of these fundamental fields. And for them, I will call them BPS ladders. So it will be, so one very nice way to organize them is to combine them into a superfield. That's just some generating function. So this is an explicit formula. Because if given one fundamental field, we can act arbitrary number of covariant derivative on it. So we introduce this bosonic auxiliary variable z, and make this, we can raise z alpha d alpha to some arbitrary power, and then sum it. And then for these BPS ladders, we can also introduce 3 fermionic auxiliary variable theta and to combine them. And they are nicely combined into this formula. And so this BPS superfield, so I call this generation function BPS superfield, and they only satisfy one condition, that is, if we set both z and theta to 0, this psi, capital Psi will equal 0. That's because it's also very easy to see from this formula. That is, I mean, the right-hand side, you just get 0 if you set both z and theta equal 0. So it turns out that it will be, using this BPS superfield, you can write down the cohomology classes and also discuss the Q-cohomology, discuss quantum correction to a Q-cohomology very easily. That's why I want to introduce this BPS superfield. And now if we consider at free point, G Young Mills equals 0, then any gauge invariant combination made out of psi will give us a BPS operator. That is because at 0 Young Mills coupling, the Q acting on psi just give us 0. And here I write down some very simple example. I can try to write this example in terms of the BPS letters, or try to use the BPS superfield to write this example. And now let's consider turning on the coupling. And at tree level, or at, in other words, at classical level, the Q action take this form. Q acting on psi give us psi squared. And this formula gives us how Q act on a single letter. And if you have multiple letters, and then Q would just obey the Leibniz rule. So these two equations will tell us how Q act on some arbitrary composite of these psis. And so the tree level cohomology, because you have a different Q action, will differ from the free cohomology. For example, this particular single trace is Q close, but at tree level, but this trace is not Q close. So this trace would be Q close at free theory, but if we introduce the tree level Q action, then this one is not. So using this Q action, we can just try to solve the cohomology classes, and for the monotone class, we actually have a closed form expression for all of them. So they take this form. So it is a multi-trace operator, And so I write it in this way. So each of these O are single trace, and they take this particular form. And you can actually check that this OM is Q-close without using any trace relation. So that so this single trace is monotone, and product of them also will be Q-close without using any trace relation. And also, if you consider infinite n, you can try to count the number of these operators. And the number count match nicely with the counting of BPS multi-particle states in the bulk. So next, we can try to consider fortuitous operators or fortuitous classes. It turns out that the fortuitous classes is much harder to find. And in SU2 theory, we have found the first fortuitous class that so that particular class emits a very simple representative taking this form. Is written in the superfield. And if you just look at this form, it's actually not easy to see why this is Q-close, and also it's not Q-exact. And so the status of Engels force binomials is that for SU2 and SU3, people have found multiple infinite towers of fortuitous classes. But we do not have a closed form of fortuitous class for all cases. And now let's try to go beyond the tree level and try to see how the cohomology vary if we turn on coupling. And in this case, people have made some conjecture. There's one conjecture that I call the strong conjecture, that is saying that the Q cohomology is tree level or classically exact. And this conjecture was first particularly made for the Engels force binomials, but you can actually generalize this conjecture to other theories, saying that it's exact tree level, or at classical level. But we can also try to make a weaker conjecture, like saying that if we try to go from weak to strong coupling, there is no this phase transition. That means, let me see, how do I explain this? Yeah, okay. This means that there can be some correction to the Q cohomology, but the Q cohomology you can go from weak to strong coupling and try to control the quantum correction without facing any place that you lose control. And
sorry, here you mean you only have one for Engels force binomials, you only have one parameter, right? What do you mean by discrete points and the co-dimensional boundary?
Okay. So for Engels force binomial, you actually have a real two-dimensional parameter space.
Oh,
and in that case, you can talk about discrete point or line. But here I try to make the conjecture more general. In some more general cases, you have some conformal manifold, and it's multidimensional. So I think this may means that this weak conjecture means that you probably only have perturbative corrections, and then you do not have this phase transition that may come from the non-perturbative correction. Okay. So for the, if we believe the strong conjecture, you can rephrase that to a different way. That is, so we consider the tree level or the classical Q, and also the tree level and classical Q dagger, and the anti-commutator will actually give you the one loop Hamiltonian. So the strong conjecture actually means that the BPS spectrum is one loop exact, in other words. And So for n equals 4 super Young Mills, there's a nice way to test the conjectures. That is to use S-duality. So as I said, that for the n equals 4 super Young Mills case, we have a two real dimensional conformal manifold. And on this space, and there are multiple free points. And we can focus on tau equals 0 or tau equals I infinity. And say at tau equals I infinity, you get free gauge group G theory. And then tau equals 0, you get a free gauge group like the Len-Len dual of G. And we can try to compute the classical cohomology at these 2 points and then try to compare them. If we get agree, then that will give us evidence for both the weak and strong conjecture. So now if we focus, the dual pair of gauge group SUN and PSUN, they have will not give us any non-trivial check because the classical Q-cohomology depends only on the Lie algebra of this gauge group. So we actually need to consider SO and SP gauge group in order to get some non-trivial check. So we focus on SO 2n plus 1 and the USB 2n. And the smallest n that you get some non-trivial check will be SO 7 and the USB 6. So this the Q-cohomology for SO and SP theory has been studied by Gadi, Lee, Reg, and Tomer. They focus on a particular subsector called BMN sector. That is, you consider truncation of the letters you can use to construct a cohomology class. So the truncation is such that the two angular momentum, J1 and J2, they are equal. And in this case, you will not get any covariant derivatives. So the problems becomes much simpler. And in this particular BMN sector, if you consider SO7 theory and this particular angular momentum and charge case, and they found that there is a fortuitous class, and but in the S-dual USP theory, there's no such class. And that particular fortuitous class takes this form. However, this doesn't mean that the conjecture is false. That is because the BMN sector is not a complete charge sector. If I fix to this angular momentum and charges, they are a BMN sector, but there are also some non-BMN sector. So we actually need to search for cohomology classes outside of the BMN sector. So that's what we did. We did a comprehensive search for cohomology classes from small and angular momentum to large, so from small charge and angular momentum to large charge and angular momentum, and we use this quantum number L to organize our search. And so we search from small L to large L. And we go up to L equals 18. So at L equals 18 and lower L, the USP6 and SO7, their classical cohomology all agree up to 2 additional classes in the SO7. So they are given in this table. So first, we reproduce their result on a BMN case. So if we focus on this particular angular momentum and charge assignment and focus on the BMN sector, and then we found out that SO7 has 1 fortuitous class, but USP6 does not have any fortuitous class. But there's and also there's another charge sector. That is by assigning the angular momentum and the R charges to this value. And in this case, in that charge sector, actually in the chiral ring sector, you found out that the SO7 theory has one more monotone class than the USP6 theory. And these two classes, they are cohomology classes in the classical Q cohomology. So they are not paired up by using the classical Q. But for their charges, it's possible that they can be paired up. But they are not paired up and lifted by using the classical Q action. So let me denote this fortuitous class by OPMN and these 85 monotone classes by OI CR. The CR just stand for chiral ring. So from this result, it's actually quite surprising that we see that the classical chiral ring is not S-duality invariant. And so let's try to understand this result. So let's try to understand this one out of the 85 classical chiral ring elements. And so the classical chiral ring of n equals 4 super Young mills are generated by the n equals 1 chiral superfields. And in n equals 4 super Young mills, we have the chiral superfield W alpha. They are from the vector multiplets. And also the 3 matter chiral superfields, phi I. And so the bottom components of phi I and the W alpha, they are exactly the small phi I BPS letter and the lambda alpha. So these are the BPS letters. And so for this chiral ring, we have chiral ring relations. They are coming from the superpotential. So we take the derivative of superpotential with respect to the chiral superfields, and this equation equals 0 gives us some relations among the chiral superfields. In terms of bottom components, there are these relations. So that means so these phi i's and lambda alpha, they are commutes or anti-commutes. And saying in other words, more abstractly, the chiral ring is given by this space. So we have 3 phi and 2 lambda. So this phi I run from 1 to 3, and lambda alpha run from 1 and 2. So we have 3 Bolzani matrices and 2 Fermioni matrices. And these matrices take the value in the Lie algebra, this curly G. So that means we have this curly G raised power of 3/2. 3/2 means that the 3 boson, the 2 fermion. And then we mod out the commutators. That's the chiral ring relation. And then, so we consider basically the polynomials of these, and then restrict to the G invariant, the gauge invariant. Yeah, sure.
So from the point of view of the theory where you had less BPS states at weak coupling, but somehow you get more when you go to strong coupling, like you have 84 and in the strong
coupling limit you get 85, 86.
Yeah. So here, if I consider SO7 perspective,
yeah,
that means at weak coupling I have more states.
Yeah, but from USP6, it seems like
it's opposite. Yeah,
there are non-BPS states which are becoming BPS.
Yes.
So does it indicate that we have to include non-BPS letters, and those might be the ones which are we usually throw away non-BPS letters and just work with BPS letters.
Right. It turns out that so these two non-trivial classes will be lifted by one loop effect. So this particular effect is just
but that's from
at the point of the SO7 point.
But from SP6 point of view, they are actually coming down from non-BPS sector.
Right.
So does it indicate that we have to be careful about including non-BPS letters, or?
I don't know. I mean, at any finite value of the coupling, you do not have that class, that particular BPS state. Only at the discrete points, only at the point that the SO7 becomes weaker coupled, you have that extra states. So yeah, maybe from the USP6 perspective, that means if you really want to describe that extra one, then the trace of letters might not be enough.
Okay, thank you.
Okay. Right. So the chiral ring has this structure. There's a common law saying that this chiral ring is isomorphic to this one. Let me try to explain this. So this curly edge means the Cartan subalgebra. And we also raise that to 3/2 power. And this WG, that's the wild group of the gauge group. And the naive argument of this isomorphism is that since all these matrices commute or any commute are mutually commuting, so we can actually use the gauge symmetry to simultaneously put them into the Cartan. So that's why we can replace curly G, this algebra, by the Cartan subalgebra. And after put them into Cartan, there are residual gauge symmetry. That is the wild symmetry. So we still need to impose the wild symmetry invariant of this polynomial. And so the right-hand side, this algebra is actually the chiral ring of the IR theory on the Courant branch. So on the Courant branch, so basically, the off-diagonal components of the matrix becomes massive. So we effectively only consider the fields value in Cartan. So we can interpret the right-hand side as the chiral ring of the IR theory on the Courant branch. And this isomorphism actually is only true if we only have bosonic elements. That means if we replace this power 3/2 by just 3 or actually any n. So if we do not have the gaugino lambda, these fermionic matrices, then this isomorphism is true and actually proven by mathematicians for both SU, SP, and SO, for all classical Lie group, and is still open for exceptional groups. However, we know that this isomorphism cannot be true, because if it is true, then the chiral ring will be S-duality invariant. That is because the Cartan subalgebra is S-duality invariant, and also the wild group is also S-duality invariant. So if this isomorphism is true, then that contradicts with our result of explicit search of cohomology classes. So in general, the statement is that there is a Biennization map from the ring on the left-hand side to the ring on the right-hand side. That Biennization map is just basically project the matrices to Cartan. And this map has a non-trivial kernel. And now with this, we have a very nice way to characterize this one out of the 85. And that is the one that if we take the representativity of that and then restrict to Cartan, we will get 0 in some good basis. And so now I have some comments. So in this SO7 example, okay, so first for these elements, we will call them non-Courant elements, because they are not captured by the chiral ring on the Courant branch. And for our SO7 USP6 example, it looks like the non-Courant element is responsible for the quantum correction of the cohomology, because for that particular pair, one element is the non-Courant chiral ring element. But it's still unknown that if this is a general feature of the quantum correction. And also this Courant versus non-Courant can actually be defined more generally for the full cohomology, not just in the chiral ring. So the way to define it is just very simple. If you have some cohomology representative, we just restrict the element to Cartan. Then you get some, you basically, then you try to see that if that element will vanish or not. If it does not vanish, then you can see that class on the current branch. So we call them current class. And for non-current class means that if you have some cohomology and then you restrict to Catan, that vanish. So that gives us non-current class. And also, actually, right now, all known fortuitous operators, fortuitous classes are non-current. That means if we take some, for the SU, I mean, we can discuss this even for the SUN cases. For the SUN, people have found multiple infinite towers or fortuitous classes. And then you can try to restrict those towers to Catan. The entire tower just all vanish. And there's a bulk picture of the non-current operator that I try to propose. That is, so say on the boundary, we try to insert some non-current operator, and then, I mean, there will be a bulk field due to that operator, and in particular, the valve of that field will be non-zero. But now we can try to go onto a current branch, and the bulk picture will be that we have a bunch of D3 branch that is parallel to the boundary. And then if this operator is non-current, I think the meaning is that the bulk field due to this non-current operator will be screened by the D3 branch. So if we consider if you go past through all these D3 branch, and then the valve will be zero. And yeah, I don't know whether this may be some properties of black hole microstates.
Can I ask a question? So when you define this Coulomb and non-Coulomb operators, does it depend
on your cohomology class, or is it independent?
You mean representative?
Yeah, Q-exact.
It doesn't depend on representative because Q-exact states or Q-exact operators, they always vanish if you restrict to Catan. So that I mean, this map is well defined.
Yeah, right. I see. Thank you.
Okay. Now let me move on to the computations of the quantum correction of this Q-cohomology. Actually, quickly after our work, two groups of people, Cho Li and Bozig and Kopp, they found one loop corrected Q, and this one loop corrected Q exactly lifts the pair of classical or tree-level classical Q-cohomology in the SO7 case. That means this one loop Q acts on OBPS, give you O85. These two groups of people, they use very different methods, but get agreement. So first group of people, they use the generalized condition anomaly, and the second group of people, they use they consider the holomorphic twist of N-equals 4 supernomials, and then do a computation in the holomorphic twisted theory. However, I mean, my feeling of these two approaches is that for both of them, there are some weak points. For the generalized condition anomaly approach, it's actually not a very systematic approach, and it's not clear that whether it can capture all the quantum correction. And for the holomorphic twist theory approach, first, it's not a computation in the physical theory, it's in the twisted theory. And also, the relation between the perturbative expansions in the twisted and untwisted theory is not very clear. So that's why it motivated me to try to come up with the different approach to compute the quantum correction. And I want this computation to be systematic and also in the physical theory, and hopefully it's a non-perturbative computation. And the idea is that for these multi-trace operators, we try to construct them by consider composites of fundamental fields. And these kind of composites are well defined classically, but quantum mechanically, there are coinciding point singularity, these OP singularities between the fundamental fields. And so that means we need to properly regularize these singularities to make the operator well defined. There's a way to regularize the singularity is by point splitting, and that is you split the different fundamental fields in the composite a little bit, and then subtract off the coinciding point singularity, or in other words, subtract off the OP singularities. So to do this, first, I want to look at what are the OP singularities we have. So let's consider the complex coordinates. These x mu are the real coordinates. Mu run from 0, 1, 2, 3, and we can combine them into two complex coordinates. So in the Lorentzian signature, actually, we do not get two complex coordinates, but we can re-rotate to Euclidean signatures. Then we get two complex coordinates. Then we have this coordinate z and z bar. In the Euclidean signature, they are complex conjugate to each other. Then we can look at what's the delta of z and z bar. So recall that delta is h minus e BPS. So that basically tells us how far away of that particular quantity away from the beam BPS. So this z coordinate is BPS, but z bar has a negative value of delta. And now, for simplicity, let's consider two scalar BPS operators, O1 and O2, and then look at what's the most general singular terms in the OPE that can show up on the right-hand side. They will take this form. It is a very general form. So the tilde means that I ignore all the regular terms. So from this form, you can see that the thing on the right-hand side can be BPS or non-BPS. It depends on its delta value. So this delta also show up in this structure. And now we can take a very interesting limit. That is, we take z bar to 0 while fixing z. And in this limit, we can actually see that all the terms with a positive value of delta will just vanish. So in this particular limit, all the terms show on the right-hand side, they are just BPS. And I will call this particular type of OPE a chiral OPE. And now, let's try to constrain the OPE singularity that show up from the psi OPE. So these psi are the BPS superfield that we introduced. First, these psi's are not gauge invariant, so we need to be a bit more careful. From our definition of this psi, maybe let me go back to here. Previously I called z some auxiliary parameter, but actually now we can identify that auxiliary z as the physical complex coordinate z. And now here we have this sum over z alpha d alpha. So that actually means that we try to covariantly translate the field from z equals 0 to some non-trivial value of z. So because here I use covariant derivative instead of the partial derivative. So the translation is covariantly translation. So yeah. So we have psi at non-zero value of z that come from the theta at 0 value of z, and with this covariant translation. And then we can split that to the normal translation and also Wilson line. So if we have some composite of psi, so this combination, even though it looks like I insert psi at different points in the z space, but actually they transform under the gauge group at z equals 0, because they are Wilson line connecting this side all back to the origin. So I do not need to insert some extra Wilson line. I can just consider this psi OP. And now by matching, and now we consider what are the most general BPS terms that you can write down on the right-hand side, and that agree with the charge and angular momentum assignment. And it turns out that there's only a single term you can write down on the right-hand side that agree with all the charge and the angular momentum.
What is kappa there?
Oh, just some constant, like
Unfixed.
unfixed constant, yeah. Okay, good. And now, now I can define the normal order operator by basically subtracting off the only terms in the OPE singularity. And that's my definition of the normal order product. And now, for this classical Q action, recall that the Q acting on psi give you psi square, and so right-hand side you get some composite. So actually, the Q action on psi should be more properly defined as such that the right-hand side you get the normal order operator. But because of this Q action in this case, so Q action on the regularized operator will not obey the Leibniz rule. So you will get a different Q action than the classical Q action. And now let's try to compute it. So let's consider Q acting on the normal order product of two psi, and let's first rewrite this psi as the usual product minus the OP singularity, and then consider Q acting on this two psi and also Q acting on the OP singularity, and you get this second line. And then with some proper arrangement, you basically want, so you can see that here, the psi's are not in the normal order product, so we need to rewrite that back to normal order product. So that's why I did here. And then these terms can be combined, and the singularity will cancel, and you get this formula. Sorry, so the singularity will not cancel here, but these two these three singular terms can be combined into a singular term. So you get the result are these two lines, and for the first line you can basically interpret that as a classical Q action, because the first line it would just take the form as like you naively just apply the Leibniz rule. So that's I call it QC, the classical Q action, but we get some extra contribution. And now we can try to take the 2 points to coincide. So this is the thing we got. And then now let's take z prime equals 0 and take a limit z goes to 0. And then we can see that in this limit, we actually get some finite term. It's not singular. And then this term will be the quantum correction to Q acting on the composite of two psi. And here, there's actually a small subtlety that is I use this interesting looking formula for taking the limits. Okay. So in summary, Q acting on this normal order product of two psi give, if you go through a computation, you get the classical Q action and some quantum corrective part. And this classical part satisfies the Leibniz rule, and the quantum correction part agree with the result from the two groups of people who compute the same thing using the generalized condition anomaly and the holomorphic twisted theory. And but I believe that my computation is much simpler. It's basically just a 1-page or 2-page computation and reproduce their results. And there are some future directions that we are thinking about. That first we can try to compute the Q action on a composite of 3 psi. And there's another interesting thing we can explore, that is to study. So now since we define the OPE, we can use this OPE, I mean, not just to compute the Q, the quantum correction of Q, but to study some other things. We can, for example, study the chiral OPE between monotone and operators and fortuitous operators. Okay. So let me conclude by some remarks. So first, we know and we have seen that there are quantum corrections to the Q-cohomology in the n equals 4 superyamules with SO7 theory, or more generally, SO 2n plus 1 theory. But now it's still unclear that whether there are similar quantum corrections in theories with other gauge group. I think the gauge group that we are the most interested in is the SUN gauge group, but for that case, it's unknown whether there are similar quantum correction or not. But the quantum correction we have seen, they are just perturbative correction, and this weaker conjecture might still be true, like there's no wall. And we can, after we control, we have some control on the perturbative correction, then we can still learn about strong coupling physics from the weak coupling. And also, final point is that this Q-cohomology is a powerful tool, and the study of fortuity has told us interesting lessons about black holes, and I think there are more in later talks today. Thank you.
Questions?
Hi.
Juan?
Yeah. So could you make a conjecture that this one loop effect that you mentioned, that's like what people call the one loop Hamiltonian dilatation operator? Is that?
No, that would be a two-loop Hamiltonian.
Oh, I see. So what you're considering is a two-loop effect.
Yes.
Okay.
In terms of Hamiltonian. Yeah.
Another question I had was, so this particular state, you never showed us, I think, what that state looked like, the extra state, right?
Right.
Is it something that if you were to generalize it to SON plus 1 or whatever that is, it's some operator which is more like a determinant, it involves n-square fields, you would expect it, or could it be like something with a finite number of traces? What could it be?
So far, we do not. So for that particular one, so far we don't know how to generalize to larger n, and we also do not know how to write it in terms of determinant or something like that. But there are actually some other non-Coulomb operators in chiral ring that can be quite easily written down. So that is, let's consider this lambda alpha, and let's consider this single trace, lambda alpha, and let's call it S. And so this operator, people have been studying the Engels 1 super Young Mills, and there are some well-known results. That is, if I raise this operator to the h power, I mean, the h is the dual Coster number, then it will give me 0, but s to the h minus 1 power is non-zero. But now if I plug in Catan, then that means so if this lambda take Catan value, then they are actually just I think in that case you can show that s to the r or r plus 1 should be 0. So that just from the fermion statistics, and
would you say what R and H are?
So R is the rank, and H is the dual Coster, and for SUN, H equals n and R equals n minus 1. So these two agree, and for if you consider SON, I think so for SON, H scale like 2n, but R scale like n. So there are some operators. They are non-zero if you do not restrict to Catan, but they will become 0 if you restrict to Catan. Yeah. So for Rose operator, you can try to study them at large n.
Hi, Chi-Ming. I was confused. Like I thought even in Konishi anomaly, it was something similar where they point splitted and when you apply Q on this gauge field, you get gaugino, and that's how you get this extra term. That's how the Leibniz rule was not obeyed. So
Yes.
yeah, like in what sense was this different from that?
Yeah. So
Or
that's
here, like-
basically how people compute this generalized cognition way. Yeah. So here you basically use the cognition anomaly. As you said that. Then the Q action given by this cognition will not obey Leibniz rule.
Yeah, but I think you said that you are trying something similar by splitting. So is the point that you can now go to higher orders or something?
Okay. So from my way, there is no loop expansion, but you can consider more and more composites.
Okay.
And it turns out that for the composite involving two psi, from my way of computing it, let's see. So this formula is an exact formula. There are no loop expansion.
Oh, I see.
But also from the holomorphic twist or cognition anomaly computation, they will also agree with me that if I consider acting on two sides, then it's one loop exact. The Q action is one loop exact.
Okay, thank you.
Hi, Chi-Ming. So in the last slide, you said that it's not clear whether for the unitary groups you'll still have quantum corrections. But I think this calculation will be similar, like whatever you've done.
Yeah, Q will have quantum correction, but the question is whether Q-cohomology will have quantum correction.
I see.
So it could be that even Q get deformed, but the cohomology is unchanged.
I see. Okay.
So, yeah, I maybe just missed something simple. When you say there's no wall, I didn't quite understand your statement. You say if there's only perturbative correction, then there's no wall. What was the precise statement?
Okay, I probably didn't. Let's see. For this wall. Yeah, I think my. So yeah, okay, maybe this term is too vague. I think, yeah. So, and what I mean is that after you if you take into account of some perturbative corrections, and then you can move away from weak coupling, and then still get the strong coupling result. Okay, maybe it's too vague. Okay,
Presumably, if the coupling is very weak and small, right?
I mean, if the coupling is very weak and small, but you take into account all orders in perturbation theory, that you already get presumably, maybe you could conjecture you get just the right cohomology and there is no change, right? There is no evidence that there is a change at any finite coupling, right?
Yes.
What you found is, you found a two-loop correction, but that means that at infinitesimal coupling, you already have a different cohomology.
Yeah,
right.
But if you have corrections to all orders in coupling, when you sum over them, then you can get the non-analytic behavior. Yeah, whether you have a perturbative correction or whether you have a phase transition, they're not directly related, right? A phase transition means you have some non-analytic dependence at some parameter, at some value of the parameter. But say if your perturbative correction truncates, then you can say maybe there's no wall. But if you have infinite series, then you cannot guarantee.
Okay. Yeah, it could be. Yeah. But if I just have perturbative corrections, then okay, you said that the sum might not be analytic.
Yeah.
Okay.
It depends on the sum. It depends on the nature of the sum.
Okay.
So this non-Coulomb-ness of the fortuitous states. So I was wondering, so if you insert operator with very large charge, large charge BPS operator, oftentimes you can approximate various computation using some semi-classics of n equals 4 supermills. Semi-classics because because it's a very large source and oftentimes it gives a web to the scalar field and some other fields. But I guess that's kind of clear if operator is a Coulomb probably. So I was wondering if the fact that the operator is non-Coulomb implies something for the semi-classics if you try to insert some large charge fortuitous states in the path integral.
So for large charge case, you can consider Coulomb and also non-Coulomb. So what's...
Yeah, so I was...
The question was just do you expect some difference? Like if you insert large charge monotonous states or large charge fortuitous states, could it be that you can do some computation in semi-classics only for large charge monotonous states, but not fortuitous states? Sorry, it's a bit vague question.
Yeah, I don't know. Yeah, this sounds interesting, but I don't know.
But didn't you conjecture previously that the fortuitous states should correspond to black holes and the monotonous states to
gravitons? Right, so the monotonous states, you could do semi-classics because it's coherent state of gravitons, like coherent states of those monotonous states. But I think you conjectured that the fortuitous states were supposed to be black holes, right? So isn't that the answer you...
So you want to say that for fortuitous states, then you cannot do such computation?
Okay, well, yeah, probably I agree.
For the large n, but I was also thinking what happens at finite n, a semi-classics of n equals 4 supermills rather than holographic duo.
Any additional questions? If not, let's thank the speaker again.